Okay, so now we're going to develop a sort of a basic repertoire of graphs of three-dimensional surfaces. And we're doing this because, well, we're going to be interested in functions where z is a function of x and y. And when you look at the graphs of these sorts of things, instead of curves or whatever, you get surfaces. And what exactly do I mean by a surface? I mean something that's really sort of like a two-dimensional object, but curved through three-dimensional space. So you can think of like an orange peel or a piece of paper or whatever. Your skin, say, that could be a surface. All of these are possible things that we're looking at in three-dimensional space. Great. So in order to better visualize and really to analyze surfaces and their graphs in 3D space, we're going to be interested in something called traces, which are the cross sections of a surface. And really, in a more mathematical sense, they are intersections of a surface with planes. And generally, these planes we're going to be looking at are going to be where we hold one of the coordinates constant. So for example, over here, these are my traces in the x direction. So these are where I'm taking x to be constant. I get a bunch of planes that are parallel to the YZ plane, and say, you know, this right here might be where x is equal to 7, this here might be where x is equal to 6, x equal to 5, etc. Y and z can vary, but x is constant. Similarly, over here, I've taken a bunch of slices in the y direction by planes that are parallel to the xz plane. You know, again, maybe this is y is equal to 6, and this is y equal to 5, etc. And we get what the plane, or what the surface looks like if we fix y. Finally, here I have an illustration of z. You know, maybe this is z equal to 1, z equal to 2, z equal to 3, etc. Just taking here horizontal planes and slicing up this mountain. Now, one way that really I see things when I look at this, especially because we're often letting z be a function of x and y, is that x and y are sort of like our coordinate system. It's like latitude and longitude or something like that. And then we can imagine our surface is sort of like a contour map, and z represents elevation, and then these lines here are our contours of our contour map, where we have curves of equal elevation. And yeah, I like that interpretation quite a bit. But the things that we're going to look at right now are not necessarily things where z is a function of x and y. So interpreting it that way is not necessarily the best idea, but for future reference, it's pretty good. So the first kind of graph we're going to be looking at is something called cylinders. And you know what a cylinder is. At least in the strict sense, it's something that looks like this. So how can we get something that looks kind of like this? Well, generally, a cylinder is going to be an equation in two variables where the third variable is free. So this guy just looks like, if I take a bunch of horizontal cross sections, just the same circle translated up and down. So that suggests that z can really be whatever it wants to be, and x and y have some sort of relationship to each other. And here I've just decided to choose the circular cross sections to have radius 1. So if I look at the cross section where z is equal to 0, that's just a graph in the xy plane, that's a circle of radius 1. It looks like I've centered it at the origin, so great, its equation is x squared plus y squared equal to 1. Now, generally, to graph something like this, what I can do is I can just take this equation and I graph it in, you know, since this is x squared plus y squared is 1, I graph it in the xy plane right here. And then to get a bunch of traces, the traces I care about here are really in the direction of the free variable. and they're all going to look exactly the same. They're all going to look exactly like this one basic graph in the other two variables. So I just take that and I translate it vertically to get all the traces over z. I sort of connect the dots. Great, I've got a cylinder. Think about it for a second, but you should realize that the traces in the x direction or in the y direction are really not super interesting. Generally, they're just going to be lines. In this case, either one line or two lines, but just nothing super interesting there. So, but yeah, so that's the general idea for graphing a cylinder. And more generally, a cylinder is just what you get when you take an equation in two variables. You get some sort of curve. Since the third variable is free, you just translate it along the axis for whatever the free variable is, and that just carves out some sort of shape in space. All right, so here is an example. Let's graph z is equal to 1 minus x squared. So my free variable here is y. So let's emphasize that y is free. So what I'll do first is I will graph z equal to 1 minus x squared in my xz plane. So my xz plane is this plane right here, and well, 1 minus x squared, that's a parabola. It has x-intercepts when x is plus or minus 1. It's going to have z-intercept when x is equal to 0, which is when z is equal to 1. So it looks something like this, and it comes down like that. And I'm going to sort of draw it dotted back here because I'm presuming that it's going to be behind the surface when I start translating it. So then let's translate it forward a couple of times, so, or maybe just once. So let's translate in the y direction, because y is free. We're taking traces with respect to y. Notice this is when y is equal to 0. So why don't we just let y increase over to, I don't know, let's pretend that this over here is y equal to 4. Why not? Great, there we go. And then let's translate it back some. Let's say up here this is y equal to -3. Great. And then we just sort of connect points that are coming from the same place. So here is what my surface looks like. It's just a parabola that's being sort of carving out a sort of like this arch shape in space. These arrows suggest that it keeps going down, but great, that's what this parabolic cylinder looks like. Okay, here is question 1. I would like you to graph the absolute value of y plus the absolute value of z is equal to 1. I don't really expect anybody to know quite what that looks like, so here I've given you the graph of what that looks like in the yz plane. It's really just a square with vertices at 1, 1, -1, -1 on the z and y axes. So sketch that, see what it looks like.